no more quizzes, and you won't have a quiz on the next chapter. That's our last chapter. In fact, we're not even really doing the whole chapter. So as you're going through and reading the chapter, realize that there are some sections that we're not covering. Let's see. I'm pretty sure we're going to have this exam. I'll let you know for certain later, and this might still change, but I'm pretty sure that we're going to have it on that 27th. What's today? The 4th? The 4th, the 6th, 11th. Oh, yeah, we'll have plenty of time. We might even have class on the 25th. We'll see. Um, we'll have the exam on the 27th. I'm, yeah, fairly certain. I'll give you the paper's due on the 2nd. Yeah. It'll be an online submission, but I also want you to bring me the paper copy so I can grade it on paper. But you bring the paper copy to me on the 2nd. Or before, if you want. I mean, of course, you can do it before. We have class on the 2nd. We'll be in the rec center. And so, you can't wear sandals. You can't wear, I don't know, what can't you wear at the sandals? You can't wear sandals. Okay. Um, okay. I'll confirm that later. But I'm fairly certain that's the way it's going to be. I have a couple more things here. Astigmatism. We talked about the different things, hyperopia, myopia, presbyopia, which is really just farsightedness, but for a different reason, that you're not because of the shape of your eyeball, but because your lens gets more brittle, not as flexible, so you can't squeeze it down as close as you can the other when you're younger. Um, Astigmatisms is because the lens is not spherical. The lens is not spherical, but instead it's oval. The focal points then are different depending on the axis. And this causes all sorts of issues, but you can account for it. So you have light rays coming in here on this part of your eye, and they'll focus at a certain point, and then you have light rays coming into a different part of your lens, and they'll focus at other points. So if I think about this as a convex lens looks like this. I have these light rays, which will focus, say, at this point, and then I have other light rays that, say, come in here, and they'll focus at a different point. And so I have rays coming in at different parts of the lenses, and they'll focus at different points. And so you get all sorts of different focal points going on in your lens, depending on where the light is coming into your eye. That's called an astigmatism because your lens isn't spherical, but instead it's more of an oval shape, or, not spherical really is the most important thing. This can be corrected with lenses that also have different focal points along different axes. So these lenses would be specially made just for you to accommodate for the different focal lengths that you have on your lens. It would sort of act to cancel that out, basically. Let's call it an astigmatism. And I think we have a few questions. Uh, we're going to skip other methods of vision correction and other problems. But if you want to do your paper on something like that, like LASIK or other types of surgical procedures for your eyes or other problems that you might encounter with your eye, that's okay. I don't think anybody's done that, but if you want to, that's fine. Let's try some of these questions, although we're going to skip one of these. Yeah, the one on the left, we're going to skip this one. All right, let's stop at 40. Okay, good. Easy, right? That's a convergent. What is it? Is it concave or convex? Convex, that's right. Make sure that you know those distinctions between the different lenses and that you can identify the different lenses. We had one on the quiz. Everybody got that one right? I think that was a plano convex. Was that right? Yeah. Okay. Hey, knock knock. Interrupting pirate. Arrgh! Okay, that's a converging lens. Okay, a person diagnosed with nearsightedness or myopia is which of these? Cannot see distant objects, cannot distinguish colors, cannot see nearby objects, or cannot focus at all. Nearsightedness or myopia. I remember farsightedness is called hyperopia. I sort of remember that because hyper is like you're extending too far, right? Like a hyperextension, hyperopia, farsightedness. If that helps you, that's great. All right, let's stop at 40. Okay, excellent. You cannot see distant objects. Remember, nearsightedness, the near refers to what you can see. That nearsighted people have near sight. They can see things that are up close, but they can't see things that are far away. Um, horse, excuse me, a pony walks into a bar. He says, "Hey, bartender, give me something to drink." The bartender says, "What?" He says, "Give me something to drink." He says, "What?" And then the pony says, "Oh, I'm sorry. I'm just a little horse." I told y'all that one? No, that question was too easy. Let's do this last one, this one right here. Which of these is the sensory layer of the eye? We'll stop at 20, 20. The other parts of the eye. Let's see. Yeah, the sensory layer, that's the layer that takes the light and converts it into an electrical signal. And so that is going to be the retina. It's sort of like the film of your eye. It's the back part of your eyeball where the light lands, the image is formed, and it actually takes that light. Your rods and your cones and the fovea and the optic disc are all on that back part of the eye on the retina. It takes that light and converts it into an electrical signal. Let's do this one. Light entering the eye refracts where? The most where? I don't know how y'all learn these different parts, but what I like to do is to, either print out or make a sketch of a thing and then just go through and quiz myself. I even get my little girl, she'll quiz me on what's this or what's that. So I find that's very helpful for me. And then also I'll maybe print out multiple copies and I'll just write it down because it really helps me to write things down. I learn them a lot better when I write them down. So you all have your different ways of learning though, so you have to sort of flesh that out. But that's what I do. Let's stop at 45. 45. Okay, good. C is right. Remember, the cornea has most of the refraction. So if we think about our eye, this is the cornea right here, and then inside the eye a little ways you have the lens. And there's refraction that occurs at the lens, but really most of the refraction occurs right here at the cornea. And then when it gets to the lens, it's just sort of fine tuning the light rays so that they focus onto the retina. Your brain fine tunes the lens by those ciliary muscles. Those ciliary muscles will stretch and push down on that lens to make your focal length change. It's really quite remarkable. And then what type of image does the retina form? Or what type of image is on the retina? Is it real, virtual, upright, inverted? I don't know if I gave this to you. We might have said it in passing. It certainly came up in your reading. It did say it clearly, right? We're sort of all over the board here. So what's the difference between a real and a virtual image? Real images can be what? Projected onto a screen. A virtual image cannot be projected onto a screen, right? Like a flat mirror. You look in a flat mirror, that's a virtual image. You can't project that onto a screen. What's the difference between an inverted and an upright image? An upright image is upside right, like in a flat mirror, but an inverted image is upside down. We saw that. Well, no, we haven't seen an inverted image, but you can get inverted images. Okay, that's a little better. I'm going to stop at 115. Oh man, that wasn't a little better. Some of you changed your answer before I did it. All right, A is the right answer. Real and inverted. Have you ever seen those glasses? You can buy them in like dorky science catalogs that they send out to us. They are glasses that will actually take the image of what you see and flip it upside down. You ever seen those before? They're glasses that turn everything upside down. Because eventually, if you wear those for long enough, your brain just flips the image right back up again. So the image that's formed on your eye is actually an upside down image. It's a real image because it's projected onto a screen. That's your retina. So if I think about my eye, here's my lens. I have an object back here. The image, as it's formed on the eye, is upside down and real. So um, you can buy these glasses, like I said, that will actually take that image and flip it up again the right direction. And it takes a little while for you to get used to it, but eventually your brain does that. Because your brain does that anyway, right? It takes this image and it flips it right side up again. Or maybe we're all upside down. Maybe it doesn't. Maybe it's just this is how we look. We're all just flipped on the side. All right, I'll tell y'all a joke, but this is a really bad joke, and it's a middle school joke, and so you have to sort of prepare. This is sort of on the edge of as far as I will go with humor. You ready to hear it? Don't tell anybody I told it to you. No, it's not machine joke. Knock knock. Smell mop. Smell mop. No, thank you. Yeah, you gotta think about it. Yeah. All right. So this very last chapter is the biological effects of nuclear radiation. Listen, most of you are probably never going to see nuclear radiation at all, but some of you might if you go into various medical fields, because you use nuclear radiation a lot for various purposes, for scanning, for treatment of various things. So I just want you to have an idea of sort of some of the basic nuclear processes, the decay processes, basic ideas about the nucleus. If you've had chemistry, which all of you have had chemistry, at least in high school, then it'll be similar to what you did there. You probably didn't do nuclear chemistry in your introductory chemistry class, but you'll be balancing equations, balancing chemical equations like you did. It'd be similar, but a little bit different. Remind you of the electromagnetic spectrum that we saw before. We've seen this in a previous chapter. Uh, Yeah, so you do need to know this for the exam, how you have the radio to the gamma ray. We've already seen this before, but you need to know how this stretches from radio to gamma ray, the different parts, all these parts that are listed, microwave, infrared, visible, ultraviolet, and X-ray, and then in order of energy, frequency, and wavelength. Energy increases as you go from this direction to over there. So does frequency, because energy and frequency are related to one another, and the wavelength decreases as you go in this direction. Shorter wavelength, higher frequency, higher energy. We've already seen that. It was in the previous chapter, but uh, just want you to be aware of that. Not all radiation, so this is radiation, this electromagnetic spectrum, but not all radiation is harmful. In fact, you know it. We're being bathed in radiation right now from the lights. There's this visible light, which is a type of electromagnetic radiation. When we talk about radiation, we don't necessarily mean that it's going to be harmful to our bodies, but sometimes it is. Let's see. I have a video I want to watch about sort of the dangers of radiation and how damaging it is. This is a Veritasium video like we've seen before. Then the next model that came about was the shell model. It helped us to understand the energy levels between the different electrons. So it turns out that electrons have these discrete energy levels as they go around the nucleus. They have distinct places where they can inhabit positions, and the shell model begins to encapsulate that. Electrons surround the nucleus in discrete shells. This wasn't really encapsulated in the planetary model. In the planetary model, your electrons just sort of move around, kind of like the planets do. But in the in this model, they have these discrete shells. So you have a place where you can have electrons here, and you have a place where you can have electrons here, but your electron cannot be here. That's not allowed. It's not an allowable position for the electron. And this came about due to quantum physics. Did a lot of experiments with atoms and studying. They would do things like shoot X-rays at atoms and figure out what the X-rays were doing when they would go through the atoms. And then in 1949, you have the nuclear shell model. And in the nuclear shell, the nucleus, or nucleons rather, describes our nucleons. That is sort of what's inside the nucleus. The nucleons, the protons and neutrons are in the nucleus. So these protons and neutrons, we collectively call them the nucleons, and these are in the nucleus. So we're going to mainly be dealing with the protons and neutrons. In chemistry, you dealt a lot with the electrons, but we'll be mainly dealing with the neutrons and the protons. And so you'll need to get a feel for sort of what the numbers mean, because we have different numbers that represent the different numbers of protons and neutrons. The number of protons, we're going to use the letter Z for that. I usually put a little thing in my Z like that. I'm not sure if y'all do that, but that's my Z. They tell the type of atom it is. If you change the number of protons, you change the atom. Right? If you have one proton, you have hydrogen. If you add a proton, then you have helium, right? So the number of protons gives the type of atom that it is. Z is the atomic number. All right. So on your, does this show up in your book? Your, it does. I don't know why it doesn't here, but so for example, that has one proton. This has three protons. This has 11 protons. That's your atomic number. And then the electric charge of the nucleus, that is the total positive charge of the nucleus, is just going to be plus Z times E. If you remember, E is that fundamental unit of charge. We had it back in the chapter on electricity, and 1 E has a value of 1.6 times 10 to the minus 19 coulombs. And that's just the unit, or that's the charge of an electron or of a proton. They have identical charges. They have very different masses, but they have identical charges. Atoms will typically, not always, and we'll see that this is the case, but atoms will typically have the same number of protons as neutrons. Usually they have the same number of protons as neutrons, but not always. And atoms that have the same atomic number, Z, but different numbers of neutrons, What do you call them when they have different numbers of electrons, like an atom? What do you call that if they have different numbers of electrons? Okay, yeah, you call them ions, but these we're going to call nuclear isotopes. So these are called nuclear isotopes. Right, so if they have different numbers of protons and neutrons, then we get different isotopes of the same atom. Bless you. All right, so it's pretty easy to remove an electron from an atom, but not so for the nucleus. All right. First of all, I want to define the electron volt because we'll be talking about electron volts. Electron volt is just a unit of energy. It's really defined as if I have a potential difference, and we talked about we had our positive and negative plates like this. If our potential difference between these is 1 volt, remember volt is energy per charge. If it has a potential difference of 1 volt, and I have an electron that moves from here to here, then it will gain 1 electron volt of energy. That's how we define what an electron volt is, and that's why we call it an electron volt. It's the amount of energy that an electron is required to have or gains when it moves across 1 volt of potential difference, an electron volt. It's just a different unit of energy. We use it in atomic processes because it helps us to think about those charges and how they move throughout the atom. The hydrogen electron is 13.6 eV, just to give you some perspective. Um, so that means that if I have a positive nucleus and then I have an electron, it requires 13.6 eV to remove that electron from that atom. And the only reason I tell you that is to show you the difference between this energy and then the energy required to remove a proton or a neutron from a helium atom, right? A helium atom has 2 protons. And so if I want to take one of those away and make helium into hydrogen, then I require a much bigger energy, 7 mega electron volts. So that's 7 million electron volts. So there's a big difference in the amount of energy required to remove an electron and the amount of energy required to move a proton or a neutron. And that's really the main point of that. Is that I want you to know what the EV is, but also we're going to be using it as a form of energy. Um, Also, we get a lot more energy because of this. That's why nuclear energy is so useful because there's just a lot of energy contained within the nucleus, much more than you would have from other processes. So, for example, if I have 100 grams of coal, that contains about 10 to the 6 joules of energy. But if I have 100 grams of uranium, it contains 10 to the 13th joules of energy. So that's what 10 million times the amount of energy in the uranium rather than the coal. And that's why, despite the various environmental issues with nuclear waste, although of course there's their own issues with coal, uh, that's why it's such a useful form of energy because there's so much of it, that there's so much of it within a sample of uranium. And this vast energy, this much different energy arises from something we call the strong nuclear force. So in nature, there are 4 types of forces. We've talked about 2 of them this semester. What were those? What are the 2 types of forces in nature that we've talked about? What's that? Gravitational force is one. What's the electric force? Okay, yeah, we talk about contact forces and normal force is one of those. But as far as sort of forces that are inherent to nature, so-called field forces, we say, forces that act across a distance. The four fundamental forces include the gravitational force, the electric force, and then two that we haven't talked about. The electric force, and then one of those is the strong nuclear force. And then there's another called the weak nuclear, which comes up. We'll deal with that later. But right now, we're mainly worried about the strong nuclear force. And the strong nuclear force, look, you got a nucleon, a nucleus. You have a nucleus. Say you got 3 or 4 protons, then you got some neutrons in there too. That's your nucleus, and then you got these electrons at various levels around it in these shells. These protons are really close together. They're much closer together than the electrons. The electrons are just like a cloud surrounding the nucleus. But these protons are very, very close together. And so you know that the electric force is just vast because, Coulomb's law is K over R squared. If R goes up, or excuse me, if R goes down, then F goes up. And it actually goes up if I were to plot F versus R, it goes up like this. So as R gets bigger, oh yes, I'm sorry, that's not right. Let me fix that. Yeah, it looks like this. So as R gets smaller and smaller, the force increases a lot, right? Because you have this inverse square law. So these protons being close together, they have a very, very large force acting upon them. So then the question arises, what holds that darn thing together? Right? If you have all these electric forces that are pushing those nuclei apart, then why are the nuclei even hold together? And that's where the strong nuclear force comes in. The strong nuclear force, I'll call it the SNF, the strong nuclear force, is the strongest of these four fundamental forces. And it is the force that binds the nucleons together. We never experience the strong nuclear force, though, because the strong nuclear force only acts over very small distances. You can sort of think of it as the gravitational force, right? That as two masses get closer and closer, then they become more attractive to one another. But it's not the same as the gravitational force. In fact, the gravitational force isn't nearly big enough to overcome the electric forces. But the strong nuclear force is. It only acts over very small distances, something like 10 to the minus 15 meters. And then if a nucleus gets bigger than this, if a nucleus gets bigger than this size, then it becomes very unstable. And that's why your bigger nuclei are not very stable because they just get too big. And then the strong nuclear force isn't big enough to keep everything together. And that's why they decay and that's why they get unstable. They'll start losing protons. Um, so if a nucleus is bigger than this, this being at 10 to the minus 15 meters, it will be um, it will be unstable and emit nuclear radiation. And this radiation is usually very high in energy because you got a lot of energy in those nuclei. You got all those forces that are holding things together, and all of a sudden they let go, and these particles just come flying out. So they're very high in energy, uh, and it's ionizing and can damage living tissue. All right. A little bit of notation that we'll need to know. I said it's going to be similar to what you saw in chemistry, but you probably didn't do this kind of thing in chemistry. Maybe some of you did. But when we write a chemical element, we'll write X, as the symbol for the element. So X is just going to be the chemical symbol. And on the next test, I'll probably give you a periodic table. You'll probably need one. Z is going to be the atomic number. This is the number of what? The atomic number, Z. It's the number of protons, right? And then A is going to be the atomic mass number. This is the number of nucleons, sort of. It's the number of nucleons. Remember, the nucleons include the protons and the neutrons. So you can get the number of neutrons, N. If you want the number of neutrons, N is equal to A minus C. All right. Often books won't include Z because Z is wrapped up in the chemical element, right? So like if this is hydrogen, what is Z going to be? If this is hydrogen, what is Z? It's going to be 1. It has 1 proton. If it's helium, this is going to be 2. If it's lithium, it's going to be 3. And so often they'll leave off that Z, but we'll put it on there. So for example, if I have this carbon with a 12 and a 6, we would call this carbon 12. You need to be able to identify how many protons or neutrons or even how many electrons it has. Um, well, how many protons does this have? It has 6 protons. And how many neutrons? How many neutrons? It also has 6. We get that. We say 12 minus 6 equals to 6. And then if we assume that it's, not an ion, that it's not a cation or an anion, then we would assume that the number of electrons would also be 6. Right? So we would call this carbon 12. We'd call it by the atomic mass number, which is the number of nucleons, the number of neutrons and protons. But you can have different forms of carbon, like you could have carbon 13. And if I had carbon 13, what would be the difference between carbon 12 and carbon 13? How would carbon 13 be different from carbon 12? It has an extra neutron, right? That doesn't change the charge, and it also doesn't change the atom, right? The element is still the same, but it's a different nuclear isotope because you have a different number of neutrons. We'll also use Z as the charge in units of E. So remember, if I want to know the charge of an atom, Z has values equal to, or rather protons have a value equal to Z equal to plus 1. That just says that the charge of a proton is plus 1 fundamental unit of charge. It's 1.6 times 10 to the minus 19. Electrons, on the other hand, are minus 1 E. Neutrons are going to be 0. They have no charge. They're neutral. And then gamma rays, well, these aren't really particles at all, so they have no charge either. That'll come up later. We'll do some chemical equation or nuclear equations. So as I said, isotopes, they all have the same number of protons, but they have different numbers of neutrons. Yeah, so carbon 12 has 6 protons and 6 neutrons, but these others, carbon 13 would have 7 neutrons, carbon 11 would only have 5 neutrons. How many neutrons would carbon 8 have? How many would it have? It has 6, I'm sorry, I put 6. Yeah, 6 protons. And if the atomic mass number is 8, that means how many neutrons? It has 2, right? You just take the difference in them. So be able to do that for the test coming up, that you can identify the number of protons, neutrons, and or electrons for an atom. All right. Um, we can do that with other elements like hydrogen. Uh, you can have H1, H2, that's deuterium, H3, which would be tritium. By the way, H1, this has no neutron, which you can tell by the notation. It's just a proton surrounded by an electron. Whereas H2, you're adding in a neutron, and then H3, you're adding in two neutrons. This has 1 neutron. This has 2 neutrons. I used to live in New Mexico, in northern New Mexico in Los Alamos. I worked there for like a year when I was an undergrad at the lab there. And many years ago, they got tritium into the water. Because you know what they did at Los Alamos, right? They developed the nuclear weapons the arsenal that we have today. And so at some point they got tritium into the water, and tritium is is radioactive. And so people that work there now, Los Alamos does all sorts of things. Like they do astronomy, they do environmental science, but the environmental scientists there would use the tritium in the water to map out the water table, because it's kind of difficult to map out where water goes underground. But when you have a radioactive water supply, you can just map it out with the radiation, the tritium. So it's kind of, that was handy, I guess. It wasn't that bad. Like you could drink the water. It was just, it had tritium in the water. Um, let's see. So molecules and atoms can be unstable because of their electron configuration. In these cases, the electrons uh, will change to find a more stable configuration. But on the other hand, like we're not really worried about electrons, we're worried about the nuclei, and nuclear stability is not the same. So y'all understand what I'm talking about, the electrons? That I can have, say, a positive nucleus, and I have these shells where the electrons are supposed to be inhabited, and I can have an unstable electrical configuration, say where I have an electron here where it's not really supposed to be here, and it can shift around, like this electron can go down to this next shell so that it becomes in a more stable configuration. Yes, you sort of know what I'm talking about? Okay, it's not that important. We're not going to see many electrons, but the nuclear stability is just different. Um, an unstable nucleus will emit radiation to find a more stable configuration. And usually they are unstable because the nucleus is too large. Remember that strong nuclear force only acts over 10 to the minus 15 meters. And if your nucleus gets too big, then that strong nuclear force just isn't big enough, doesn't act over that such a long distance, 10 to the minus 15 meters, to hold that nucleus together. So when this happens, the strong nuclear force can't hold the nucleons together. All right? All nuclei with an atomic number bigger than 82, that means 82 protons, uh, and by the way, that's lead of Z equal 82. All of those that are bigger than Z equal 82 are unstable, just because their nuclei get too big. And for an atomic mass of less than 40, that means, roughly 20 protons, stable nuclei of about the same number of protons and neutrons. So for example, C12, carbon 12, has about 6 of each that we've seen before. So all nuclei that are bigger than 82, that have more than 82 protons, those are unstable. And then some nuclei that have Z less than 82, they can be unstable if they have unequal numbers of protons and neutrons. Not all of them, but if you have unequal numbers of protons and neutrons, some of those can be unstable and they can actually be radioactive. Like they can emit radiation to find this new stable configuration. Okie dokie? Now with me, sorta, kinda? Lead is not unstable, right? So it's not radioactive. That's why you often, let's see, is it because of the density? I think it's because of the density of lead. That's why you use lead like for, to shield from radiation. When they put the thing on you at the dentist, that's a lead piece of lead that shields you from the radiation, but not radioactive in itself. Okay, so there are different types of nuclear radiation. As I said, they emit this radiation when they are unstable and decay. And then we have three types of decay. All right, we have alpha, beta, and gamma decay. Sometimes, like I said, you'll see the Greek letter alpha, beta. Sometimes you'll see the Greek letter beta, and then gamma decay. You need to know what each of these three are and how they work. Your book goes into this and describes them and gives some examples, but I'm going to give lots of examples too. Gamma, by the way, looks like that. That's the Greek letter gamma. So sometimes you'll see those Greek letters, but I'll write them out on the test. So you have these three types of decay, alpha, beta, and gamma. And in decay, when this happens, remember you're going from one unstable configuration to a more stable configuration. Sometimes you can actually have a chain of events. You can go from one stable configuration to another that's slightly less unstable to another that's even slightly less unstable from that. But in decay, one nucleus or a nucleus is changed and may become a new element. And the parent nucleus, we call that's the original nucleus, because I'm going from one type of element to another, and the parent is the original one, and then the daughter nucleus is the nucleus that results from the decay. They don't have to be a different element. In fact, we'll see some where they're not a different element, where all we're doing is we're emitting a gamma ray, but it changes sort of your energy state. So if all I emit is a gamma rays don't have charge. They're neither positive or negative charge, so that doesn't change the element. Or likewise, if I'm just emitting a neutron, that's not going to change the element either. But often we will. We're going to write the nuclear decay equation. You're certainly going to have these, a number of these on your test where you have to interpret them and know what they mean. And the nuclear decay equation will look something like this. It'll have your element, whatever element it might be, carbon, uranium, plutonium, whatever it is, with your numbers here, A and Z, your atomic mass and your atomic number, and then it goes to some new element. I'll just call this X prime, A prime, Z prime, plus some radiation. And remember, radiation can include my alpha, beta, or my gamma rays. My alpha or beta particles are my gamma rays. So I say radiation, but we are including those alpha and beta particles, which are really, they're just tiny little particles that have a lot of energy. Okay, and this radiation may be alpha or beta particles. or maybe gamma rays. You might also get other types of radiation, but we're not going to deal with those at all. The decay equation only goes in one direction. I know in chemistry, sometimes you get chemical equations where you can go back and forth between them. Maybe you have to put energy into the system, but you can go back and forth. This only goes in one direction. It doesn't work that way. And a couple rules. We'll wrap up soon, but let's just get these rules down. The number of nucleons, remember A is the protons plus the neutrons, is conserved. We're not going to go losing nucleons around the place, okay? We got to keep all those nucleons accounted for. The number of protons and neutrons in the parent, then we go from parent to daughter in this decay process, must equal the number of nucleons in the daughter and the radiation. So whatever our radiation particle is, you have to include that in your conservation of nucleons. So your number of nucleons is conserved. And then the second rule is that the number of protons must be conserved. In some cases, the nucleus will change the atomic number. That's my Z. And that becomes a new element. Like I go from hydrogen to helium, for example. If this happens, the decay radiation must have the lost protons. Remember that decay radiation is a particle. It's gamma rays are radiation in the way we think of it, but often alpha and beta particles are types of particles. So if that's the case, if your nucleus lost a proton, it has to be in this lost, must have the lost protons. All right? So let me look at our schedule right quick. Give me just a second. Today is what? It's the 6th? Okay, so we have 1, 2, 3 class days. Don't leave yet. Just give me a second. Listen, I'm pretty sure we're going to finish this up next time. And so I'm pretty sure that we will definitely have our exam on that next to last class day, not on the, not in finals week, but instead we'll definitely have that exam on April 27th. Bless you. Definitely have that exam on April 27th. And likely we won't have class on the 25th. So I'll be here, of course. So if you want to come in on the 25th, like we can just sort of review for the exam, but we probably won't have class. But I'll let you know of that next time. I think we'll finish this. I'm fairly certain that we will. Okay, read this chapter. It'll make a lot more sense to you if you come in having read the chapter. But we'll do a lot of decay equations next time.